Every offshore oil rig operates under constant assault, extreme pressure, corrosion eating through steel at 0.5 millimeter per year, storms, and millions of potential failure points. Yet catastrophic blowouts remain statistically rare, not because failure is prevented, because it's expected. The system is not built to avoid failure. It's built to decide how failure happens. The question is, what that decision actually looks like and where it breaks down. Steel on an offshore rig is in a state of permanent retreat. In the Gulf of Mexico, corrosion strips away 0.3 to 0.5 millimeters of metal from exposed surfaces every year, even with coatings and cathodic protection. This loss is not a hypothetical risk, but a quantifiable, measured fact. Design codes respond by building in a corrosion allowance, typically 10 to 15% of the original wall thickness, multiplied by a safety factor between 1.25 and 1.5. That margin is not a buffer against the unexpected. It is an explicit admission that the environment will win, given enough time. Engineers do not pretend to eliminate this process. Instead, they treat uniform material loss as an input variable. Inspection regimes are calibrated against these rates. Ultrasonic thickness testing is scheduled to catch wall loss before it reaches critical thresholds, while acoustic emission sensors now detect cracks as small as 0.5 millimeter, months before they become visible. In high-consequence zones, these sensors provide a 6 to 12-month window for intervention, but they do not prevent degradation. They simply reveal it early enough to allow for managed collapse rather than sudden rupture. Even the most advanced coatings and alloys can only slow the pace. Residual corrosion persists in crevices, under insulation, and at welds. Fatigue from wave-induced loading accumulates in parallel, compounding the risk. The result is a system that does not chase the illusion of zero failure. Instead, every critical component is designed with the expectation that it will lose strength, that cracks will initiate, and that inspections will find damage before it becomes catastrophic. The baseline is not perfect prevention. It is continuous, measured loss, managed by engineering logic and probabilistic thresholds. Offshore safety is built on the premise that failure is not an exception to be avoided, but a process to be monitored, quantified, and contained. Offshore oil rigs are governed by a taxonomy of controlled failure, a vocabulary that defines not just what can go wrong, but how, where, and with what consequence. 3 terms shape this logic: fail-safe, fail-operational, and fail-contained. Each describes a deliberate engineering choice, not an accident. A fail-safe system is designed so that when a fault occurs, it defaults to a condition that minimizes hazard. Pressure relief valves are a classic example. When internal pressure exceeds a set threshold, the valve opens, venting fluid safely rather than allowing an uncontrolled rupture. Fail-operational systems, in contrast, keep working despite a fault, though often at reduced capacity. Redundant control lines or dual hydraulic pumps allow a rig to maintain partial function if one path fails, buying time for intervention. Fail-contained logic isolates the failure to a defined boundary, preventing escalation. The emergency disconnect package on a drilling riser, for instance, severs the connection between the rig and the well if structural integrity is lost, confining a blowout to the seabed. The 2009 Montara blowout in the Timor Sea is a documented breach of fail-contained logic. When the primary well barrier failed, hydrocarbons escaped beyond the intended containment, resulting in a sustained release that continued for 10 weeks. These categories are not theoretical. They are codified in API Standard 53 and referenced in every well control plan. Every pressure boundary, every control circuit, every containment manifold is assigned to one of these modes. This classification does not eliminate failure. It dictates the manner and extent of its impact. The blowout preventer, which will be examined in detail next, often combines these logics, designed to fail safe through hydraulic closure, fail operational with redundant actuation, and fail contained by isolating the well from the environment. Offshore safety is not about the absence of failure, but about engineering its boundaries. The blowout preventer is the last mechanical decision point in offshore well control. Its logic is not to guarantee containment, but to decide the manner and limits of failure. The system is not built to avoid failure. It is built to decide how failure happens. A BOP stack is a composite of engineered boundaries. The stack includes annular preventers, pipe rams, and, most critically, the blind shear ram. The anatomy is defined by API Standard 53. The stack must close within a window of 10 to 90 seconds, with accumulator energy capable of sustaining at least one full stroke actuation. This accumulator stores hydraulic pressure, delivering the force that drives the rams shut. The minimum requirement, 30 seconds of stored energy, reflects the need for a backup actuation even if the primary hydraulic circuit fails. The control pod is the system's nerve center. It transmits commands and status at 10 Hz, with a benchmarked availability of 99.91% for at least one well control function. This high reliability is not a guarantee of success, but a statistical measure of how often the system remains responsive under stress. Each function, shear, seal, disconnect, is monitored and can be actuated independently, but the system's true limit lies in the physics of the hardware. Shear rams are tested in the lab to cut standard drill pipe at 30 to 33 kilonewtons, yet field specifications call for 45 kilonewtons to sever deformed or offset pipe. In the Macondo forensic analysis, the delivered force fell short. Misalignment and pipe deformation widened the ram gap, and hydraulic leaks reduced available pressure. The result was that the shear ram closed only partially, leaving a residual flow path. This outcome was not a random failure, but a quantified endpoint within the system's designed envelope. The BOP's containment logic is measured, not absolute. Every element, ram, accumulator, control pod, operates with a defined probability of success. The architecture does not seek perfection. It quantifies the limits of engineered containment, accepts the existence of failure, and channels it into predictable, bounded outcomes. This is the hardware reality that anchors the taxonomy of controlled failure before any human interpretation or intervention begins. Inside the control room, the operator's role is not to command, but to interpret. Pressure readings, flow rates, and valve positions arrive as a stream of data, filtered through layers of sensors and alarms. Each signal carries uncertainty, noise, latency, and occasional contradiction. During a well control event, alarms do not sound in isolation. When more than 5 critical alarms trigger at once, the average response time stretches from 6.2 to 13.8 seconds. This window is not theoretical. It is measured in post-incident studies and embedded in training protocols. In 71% of surveyed crews, dual failure scenarios, where both primary and backup paths are compromised, have never been practiced. One operator, interviewed after a documented alarm flood, put it plainly: "You don't decide what's real. You decide what to ignore first." Human latency becomes another variable in the risk equation, a time cost that is measured, modeled, and ultimately traded against production efficiency. Each second of hesitation narrows the margin for mechanical intervention, reinforcing that the operator is embedded within the system, not above it. Operating an offshore oil rig is a financial calculation as much as an engineering one. Each day, a well sits idle costs between $500,000 and $1 million in lost production. This figure does not include penalties for missed delivery contracts or the ripple effects on supply chains. Inspection and maintenance routines are not dictated by the theoretical ideal, but by the economics of downtime. Risk-based inspection intervals, for example, are set from 2 to 7 years, depending on the calculated probability of failure and the asset's criticality. Shorter intervals increase safety but multiply costs, while longer intervals save money at the expense of a higher chance of undetected degradation. Management is tasked with deciding exactly how much risk to tolerate, how often to inspect, how much redundancy to add, and which failures are acceptable within the operating budget. The result is a system that embeds a non-zero probability of failure, not as a flaw, but as a cost-controlled feature. The safety margin is not infinite. It is bounded by the price of lost production and the diminishing returns of additional safeguards. Every safeguard, every inspection window is a product of this economic ceiling, not an engineering ideal. Redundancy on an offshore rig is not a guarantee of safety. Each additional safeguard, whether a backup sensor or an override circuit, creates new pathways for error. In industry incident data, alarm flood events, where more than 10 critical alarms trigger simultaneously, occur in 12% of reported cases. The intended logic is clear. More alarms should clarify, not confuse. But when the system floods with warnings, operators face a rising cognitive load. Analysis of incident clusters shows that the rate of manual overrides triples once alarm counts exceed 5, as crews attempt to silence what they perceive as noise. The Macondo well timeline illustrates this paradox. On April 20th, 2010, the control room registered 9 active alarms, each requiring acknowledgement. The standard 9-item checklist was ticked off in sequence, but the surge of signals blurred the distinction between genuine failure and false positive. Monte Carlo sensitivity models confirm the effect. When alarm response is delayed beyond 300 milliseconds, the probability of loss of control rises above 1 in 1,000, a 10-fold spike over baseline. The result is a system that nears the edge of a self-amplifying cascade, where redundancy breeds complexity, and complexity accelerates the route to failure. In offshore engineering, failure is not an exception, but a baseline parameter, managed, partitioned, and priced in. Every safeguard introduces new complexity and new failure paths. Operators interpret the system. They do not command it. The lesson persists. Absolute safety is an illusion. Only the architecture of controlled failure remains real.